Welcome back. Next up, we have Kristine Bauer giving the second lecture in her lecture series.
Okay, so as yesterday, that QR code will take you to the notes for this lecture. If it turns out that you want to be able to follow along, if I'm going too fast, then those are there. They're by no means perfect. It's just something to help get through the lecture. Okay. So let's just remember where we were at the end of last lecture. So what we concluded yesterday was we had selected excisive as the underlying notion for linearity. We just find a linear functor to be both excisive and reduced. We defined these helping functors t so that each power t to the kf is just a little bit more excisive than t to the k minus 1f. This, I'm gonna write on these slides and I need to keep this thing here, but I'm sorry it's a little bit in the way. Hopefully it won't cause too much trouble. And we defined P1F as the best excisive approximation of F. I said there's some outstanding work here because I didn't actually show you it was excisive. I only showed you that if F is stably excisive, then P1F is excisive. And we'll get to the rest of that today with the rest of the degree n functors. Okay, so I did realize in the question period, oh, you know what I can do that'll avoid that thing? Let's try that. Okay. I did realize in question period, haha, I'm so Canadian now, we have a question period in Parliament, no. Okay, I did realize in question period, oh my God, I can't not say it, that I had conflated the idea of linearity being excisive with the idea of linearity being excisive and reduced. And so I just want to sort those out once and for all now by making a couple of definitions. So I'm going to just define P0F to be the value of F at the base point. If you remember, all my categories had base points. I'm going to keep doing that because it's easier that way. And then P1F is just what P1F is. It's the homotopy colimit of the T's. There's a natural map from P1F to P0F. You can think of that as just being the map to the terminal object, but after I've applied the functor, it's at least induced by that on the T's. And then D1F of X is the homotopy fiber of that. So the one that's linear is D1. That one is both reduced and excisive. The fact that it's reduced is immediate. Take the T's and evaluate them on F of star. You're going to get a base point every single time. And so D1F has no choice but to be reduced. And then it's excisive basically because it's a homotopy fiber of excisive functors. I'm going to use that term several times today. All right, so just like I started yesterday with a thought exercise about what does it mean to be linear, I want to start with a little bit of a thought exercise today about what it means to be polynomial, but I have a preferred answer, so I'm not going to dedicate the time to this that I did yesterday, because I know a way that we can go off the rails here and not go the direction that I want. So I'm going to control it a little bit. And I want to think about the fact that when we're talking about functions, a degree n polynomial function is determined by its value in n+1 points. And that's a good motivation for the way that we're going to construct the PNs. All right, so just to repeat my setup, I'm going to change my setup a little bit too, so that's the other thing. So I'm just going to simplify and say C and D are both base pointed homotopical categories and that they have all limits and colimits. I don't need all of that, that's a little bit of overkill. But it's easier to just say that instead of specifying the difference between the two categories. In particular, yesterday, I think I didn't assume C to be homotopical. Tomorrow I'll explain why. And then I had homotopy functors, so that was not, they don't go together. Okay. We want to assume that sequential colimits in C commute with finite limits. Some of you know that hypothesis by a nickname called differentiable. It's the same thing, I'm just not going to use the word. And then I want to have a homotopy functor. All right. So let's think about what it means to be polynomial degree n. I've left space on this slide, but I don't remember what I'm supposed to tell you. So just give me a second. Okay. So this is our main example. And if f is excisive, then what do I mean by saying that it's good motivation to say that a polynomial is determined by its value on endpoints? Well, in our main example, my functor was the value of if f is excisive, then the value of f at x is determined by its value on 2 points. You can't see it, I can fix that. In this case, I mean 2 copies of the map from x to the point. So just remember that in my main setup, my 2 copies of x to the point are going to fit into a diagram like this. Okay, so that's kind of step 1. I complete this by taking a homotopy cofiber, which I might do by replacing those points by cones. If I'm thinking about spaces, and we'll talk later about what my cones might be more generally, but you can just think of that as a cofiber replacement for the point. Take my push out. And then, of course, I'm supposed to apply f to the whole thing. Well, I'm going to find it more convenient to think about this as a point again, so I'm going to forget about the fact that I replaced somehow to take, took a cofiber replacement of my point to take a strict push out instead of a homotopy one. And so the value of this was really determined by this diagram that was just these 2 points to begin with a map from x to them. That's the way in which I want to think about my polynomial function. Because, sorry, I should have said that because this is excisive, this thing is supposed to be a homotopy pullback. So I've determined f of x up to homotopy just by starting with this diagram that has this map from x to 2 points. Okay, so that's the way in which I want to think about my functors as being determined by 2 points. And I can iterate this to form higher dimensional cubes. So maybe I didn't, maybe I don't want to draw an n-dimensional diagram on a 2-dimensional space, but I'll do 3 and then we'll see what happens. Okay, so I could have started instead with 3 points. And I can do exactly the same process. Okay, take the homotopy push out of this, but I'm going to make sure that this homotopy push out is done in a very intentional way. What I'd like to do is make sure that I push out along any 2 maps at once. So every face of the cube that I'm building will be a homotopy push out. I forgot to put a cone here. There it is. Okay, there's one back there that I've not put in a good place. We'll just move this over a little. And then what should go here? Well, if I'm thinking topologically for a minute, then what I have to do is glue together 3 cones along a common copy of x. We have a name for that. It's the join construction. So you can think about this as taking my 3 points. I think I want to call them 0, 1, and 2. Take your 3 points, throw them out into space someplace, and then take a line from that point to each point in x. Okay, that gives you a cone, and I'm just going to do it 3 times, and I get this 3-fold join. And so this construction in spaces is going to be motivation for the thing that we want to do in general. I'm going to move away from spaces today, but I think it's important to think about this one. And then what I want is to ask, when is f of x the homotopy limit of the resulting diagram? All right, so just to make it a little bit more clear how I'm going to set this up, let's notice that my cone on x is the join with 1 point, which I'll call 0. My cone on x here is also the join with 1 point, but I'm going to give it a different name. All right, so to it, I'm doing this 3 times, and I've given everybody an appropriate name. And I'm a little bit concerned that I'm gonna need to move things over, so just let me move this a bit, give myself the space I need. Okay, so there was an F. There was an X star 3 points here, once upon a time. And then my unreduced suspensions, well, those are the joins of 2 points, but if I do it this way, then I can make it really clear which 2 points I'm joining with, so that's what the labels are for. Okay. And this is F of X star, these 2 points, 0, 1. Read that. And then down here I have F of X star, whatever's left, which I think is 0, 2. Okay, we've just set it up in a way that we can make it clear that we're keeping track of who's who. And then, of course, there was the last one, which doesn't really want to fit anymore. We'll just say it was F of this. Okay. Okay, and we can ask, when is F determined by the rest of the cube? In other words, when is this diagram a homotopy limit diagram? Okay, so with that motivation, that is what I would like to propose as the idea of what it is that I want to think about as polynomial degree n. I just told you how a functor could be measured to be determined by its value on n points, and that's kind of what we're after. And obviously I can do this with higher degree cubes, I just can't draw them, so let's not try to do that. Let's make some definitions instead. All right. So let's let n be the set from 0 to n that has n plus 1 things in it, just like when I did my the thing that's going to be degree 2. Did I screw up the n's? This one's going to be a degree 2. So a degree 2 polynomial is determined by 3 points, and I hope I got that right when I said it the first time. Okay, good. I was a little worried. Okay. So a degree 2 polynomial is going to be determined by 3 points. So here I'm going to have my n having n plus 1 points. A degree n polynomial is going to be determined by those n plus 1 points. So an n cube is just a functor from the power set of that set from 0 to n into C. And here I did screw up who is called who. Let's see. That one was called a 3 cube. So this one is supposed to be called an n plus 1 cube. Okay. The rest of them, it doesn't matter because they don't depend on a relationship between an n and somebody else. An n cube is called Cartesian if it's a homotopy limit diagram. So if that whole thing, if the f of x is determined by the rest of the diagram. And it's called strongly co-Cartesian if every face of the cube is a homotopy pushout, which is what I did when I was defining the way that we put those cones together to get the whole thing at the end. Okay. Yesterday I said strict when I should have said strongly. Greg asked me about it and I just couldn't even hear the question. Like I didn't understand what was being asked. So I have arranged in many cases to be able to take strict pushouts by taking a cofibrant replacement. But all I need is for each face to be a homotopy pushout. I don't need things to be strict. All right, so now what I want to do is try to get away from thinking about this in terms of spaces and instead just think a little bit more categorically. So I'll give you 2 perspectives on how you can replace those joins that we talked about that were very space dependent with things that might happen in a model category or an infinity category. Okay. So the first thing is, so Nick Kuhn wrote down how to do Goodwillie calculus in a model category in general. And so in Kuhn's paper, his construction of my join, so I like maybe this should be in quotes now because it's not the actual join anymore of topological spaces and sets. It's just the thing that's going to be the join in our model category. So he said take the homotopy cofiber from the coproduct of U copies of X to itself. Okay, so why should that thing be a replacement for what we're doing? Let's just look at what happens on the case of 2 copies of X. Okay, so here's 2 copies of X. This is supposed to be the fold map. And so if I'm in a model category, what is the natural thing for me to do when I'm folding? Well, what I should do is I should, because I want to take a homotopy cofiber, I should think about replacing with something up to a cofibration, and I'm going to choose my cylinder object as the way that I'm going to get that cofibrant replacement. So I've drawn this as though it's an actual cylinder. If you're familiar with model category yoga, then you know that I can always do this even if the picture isn't an actual cylinder. And this thing is, of course, equivalent to X. What's the homotopy cofiber of that? Well, it's the thing that I get when I kill the 2 copies of X. Oh, there's my suspension showing up. So here's my 2 copies of X. They map in at the top and the bottom, and then I killed them. Very violent part of the talk. Okay. Now, if you're thinking infinity categorically, I think that's an adjective. Yeah, okay. If you're thinking infinity categorically, then this construction isn't going to make a ton of sense. So Jacob Lurie has a way of thinking about what this should be that requires constructing a confibration. And I made a decision at some point that telling you what that was exactly was going to take me away from the main thread. So I will just say that basically the idea here is to construct a functor that has to have the property that when I take the join with the empty set, I just get X. If I take the join with any 1-point set, then I get a point, a terminal object, but my categories are base pointed. So I'm going to call that star. And then if I wanted to do something with 2 points, then I just use the fact that a 2-point set is made out of 2 1-point sets. Just like I did in the cube that I constructed before. And I will define what it means to be X join 2 points by just taking the strict, or sorry, taking not strict, we're in an infinity category. The homotopy colimit. For some reason, I changed that guy's name. No, I don't want to go to the link. I want you to do that. Okay. And so that's the essence of what that construction does. It's not really different than what I did before. It just says start with something that is the identity when you join with the empty set and the terminal object when you join with 1-point set, and then everything else falls out of it. Okay. Great. So now I have a very general way of thinking about how to construct these n cubes. And so now I just iterate, not iterate, but I just imitate the construction that I did yesterday. So I have a functor that tells me how to, so this thing is really shorthand, right? This looks really small and like compact, but that's really an n-dimensional cube. And so what we do is exactly the same thing that we did. We populate the cube by taking these joins, which have the property that each of their faces are pushouts. I hit the thing with F. I take the homotopy limit of that. That's my T. And the idea of this is just like yesterday, that whatever n-excisive means, this should be a little bit more n-excisive than whatever F was. There's a canonical map comparing F to TNF. We'll need that a lot, so it has a name, little TNF. And then to get the n-excisive approximation, I just make that into a tower by iterating Tn and take the homotopy colimit. And the idea, just like yesterday, is that because each of those iterations of T is a little bit more close to being n-excisive, that by the time I take the colimit, I produce something that's actually excisive. Okay, so just as a sanity check, does this go with what we did yesterday? Well, the first thing is that T0F is going to be a point for the reasons that I didn't write that down very well. So why is t 0? And I didn't leave myself any room to do it, so we'll put it here. So why is t 0 a point? Well, t 0 is a point because it's trying to look at the cube f of x star empty to f of x star 1 point. And the process says delete the first guy and take the homotopy limit of what's left. The homotopy limit of this is just whatever this is, but we specified that this is f of a point. So t 0 does what it's supposed to do. This makes the construction I told you before about d1 a little better. And t1 does what it's supposed to do because in fact, that is exactly a generalization of t1. So we just compute exactly the same thing we did yesterday. Okay. Great. Okay. So now I'm going to show you that PNF is n-excisive. In the case n equals 1, this will complete the uncompleted work from yesterday. And I'm just going to give you an idea of how this goes. And the main idea is this lemma that's due to Rusk. So the idea is that, are you shaking your head because it's due to Goodwillie? Yeah,
the proof,
so
a simpler proof is due to Rusk.
yeah, that's right, exactly. So the lemma is due to Goodwillie and the proof I'm going to show you is due to Rusk, and thank you. So the idea here is that if I start with a strongly co-Cartesian n cube, then the map of that I get of n cubes by just doing TNF at each vertex. So what I really have here is f of some co-Cartesian n cube here. Again, it looks nice and compact, but it's really an n-dimensional cube. And at each vertex, I hit the other one with TNF, and I get a map between them using the little maps TNF. The lemma says that that thing always factors through a Cartesian n cube in D. Yeah.
Can you say what you mean by n-excisive again? Because I know you said yesterday something about being stably excisive, which was the other one being excisive in a certain range. So
Yep.
Can you say how this is different?
Yep. So n-excisive means that when I take, oh, where'd they go? At some point I put the definition, but maybe I did not. That was an oversight. I'm sorry. So being n-excisive was described on this slide, but I forgot to put the actual definition. So it means that if I take a strongly co-Cartesian cube and I hit it with F, then the resulting thing is a Cartesian cube. Okay, so let me correct that by putting the actual definition on here.
Are they not related in some way?
The definition from yesterday, the
Like
stably one.
stably, yeah.
So let me finish this and then I'll answer that question. N plus 1 cubes to Cartesian cubes. So the stably meant that if it turned out that I knew that the initial map, so stably is only going to work when it turns out that I'm talking about something like top. Okay, and when I'm talking about something like top, then I can say, okay, well, if these maps are connected enough, then the map from this to the pullback is predictably connected, and those things grow as it turns out that I iterate the T. So that's the stably n-excisive property, or part of it was the stably n-excisive property. But the actual, even yesterday, the actual condition of being excisive meant that if I started with a push-out diagram, I had to take it to a homotopy pullback diagram. And so now I'm doing the same thing, but it has to take these strong co-Cartesian things. And again, I'm going to try to not work so much in top today. I'm going to keep going back to top. I'm not going to lie to you, like, spoiler alert. But that's the idea. Okay, sorry for that oversight. All right, now where were we? Out, blah, 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 and there's my lemma. Okay. All right, so we want to prove this lemma. I don't apparently really want to prove this lemma, but I will get there. There's the construction. Okay, so here's what we want to do. Okay, so my goal now is to say that, okay, if I have a map F of chi T and F of chi. Yeah. I'm being fussy in a way that I shouldn't. F of chi to T and F of chi. Factors through the Cartesian cube. When chi is strongly co-Cartesian. Okay, so that's what we're trying to prove. So what I want to do is remember that this thing, I mean, it's sitting here looking all innocent, but it's actually a big ol' n cube, the same as before. And so now I'm going to make a new n cube. Okay, so for each subset, V. Well, I'm sitting in, let's assume I'm in n+1 cubes. I didn't say it, but let's make these things n+1 cubes so that V is sitting in n. Define a helping function, chi V, from P of n to C. Which is defined as follows. So chi V of U is, so chi V is going to be this, whatever n cube, size of n cube I started, chi V is the same size of n cube. And what I do is I just take chi of U union V. I promise these are chi's, not x's. Okay, so what does that thing do? I just want to show you one of these cubes. So we're going to take n to be equal to 2 because I can't draw any higher than that, and v to be equal to 1 because it is. Okay, so I might start with a cube chi v of the empty set, mapping to chi v of 0. I'm going to not put the brackets on because then I can write faster. So that's really the subset 1 of 0, 1, 2. This is the subset 2 of 0, 1, 2, and it just takes a long time to draw cubes. Okay, there's another face back here. That I welcome you to finish. All right, so my regular cube chi would look a lot like this if I just removed the v's, right? So I just had some functor that's going to have some value on each one of those sets. Now, what does v do to it? So what this is going to do is now I take the union with 1 at every vertex. So the empty set union 1 is just 1. 0 union 1 is 0, 1. 1 union 1 doesn't change. This map just got turned into the identity. We can keep going. 0, 1, oh, sorry, I've added v's like I'm doing this twice. Okay. 0, 1 union 1 doesn't change. This map just became the identity. This becomes 1, 2. This becomes 0, 1, 2. Yeah.
Should that have been 1, 2, the first word?
Yeah, probably. That's good because that was supposed to be an equals map and I was getting worried. And this one is 0, 1, 2. Okay, and you can check if you filled in the vertex appropriately before, which obviously I'm prone not to. I believe this one was supposed to be chi of 0, 2, and now this is a 0, 1, 2. So all of these forward pointing maps just became the identity. And what I have now is a co-Cartesian square that's really, really co-Cartesian, right? Like some of those squares are so co-Cartesian that they're pulling back identities to identities. So it's not like, I feel like we shouldn't, you know, maybe there's another name like super strong co-Cartesian square or something, but the point is that this co-Cartesian square doesn't know much that the first one didn't, and it's really just the limit of this thing is just going to be the limit of one of the faces. So it's sufficient to kind of move down a degree. Okay, so here's what I want to note. The resulting square has two equal faces. Chi v is still strongly co-Cartesian. As I said, it's super strongly co-Cartesian. And what I'm going to do is, is define y of v to be the homotopy limit. It's just going to be y of v now is going to be the homotopy limit of the cube where you just remove the empty set. Okay, so just now we've made all of these same cube diagrams. Some of them are not very new, if you already knew what the old cube did, and we just replace this. So this is just going to be the homotopy limit over everything except the empty set. Chi v of u. All right. So y is in fact our Cartesian. And it factors f chi to tf chi. I almost left myself enough room on this slide to do this. So I didn't show you why it is that factors, but if you try this on our favorite cube, what you'll see is that the y cube doesn't actually change very much. It takes our original cube and it's the identity most of the time, but it changes the 0th vertex, the empty set one, to t. And so on our favorite cube, it's the identity most of the time, and it's the map to t on the last one, and then the rest of the vertices map to tf the way that they did before. So that's the factorization. And why is that thing on our favorite cube Cartesian? Because that vertex t that we just replaced it in, that's how it's defined. It's defined to make that middle cube Cartesian. So in the special case of our favorite cube, it works really nicely and easily. Okay, and then that turns out to be true no matter which co-Cartesian cube I started with, because of the fact that t has that property that is defined that way. Okay. Now, that tells me what the lemma is. Now, how do I prove that P and F is n-excisive, which I don't have to write again because it is the banner of the slide. Well, to prove that P and F is n-excisive, what I'll do is I will compute Pn F of a strongly co-Cartesian cube and prove to you that that's going to come back to a Cartesian cube. Okay, well, how do I do that? I just take the definition. All of these have little n's in them because I'm really taking Pn. And I keep going. But I just proved in the lemma that I can factor this. So in the limit, I get Pnf as the homotopy colimit as this. I just proved that I can factor each one of these through some Cartesian cube. Why did I prove I can do the second one? Because it's just t of the same thing, so by functoriality, I'm gonna get the same thing. Instead of taking the homotopy limit of the top, I can take the homotopy limit of the bottom. That thing is going to turn out to be Cartesian. So that's the proof that PNF takes strongly co-Cartesian diagrams to Cartesian diagrams. Now, if you just take the case n equals 1, then you get that P1F is excisive, which is the thing I promised you I would tell you yesterday and didn't tell you till today. Yeah.
Why you, diagram is Cartesian?
It's just because everything in this is Cartesian that it's gonna work out. You're right, in general, this is not true. But remember at the beginning, I said that I wanted, oh, I think I said it in the wrong category. I said I wanted sequential co-limits to commute with finite limits.
Oh,
So I have to have that, and thank you for pointing out why I had each one of my hypotheses, because I forgot to say it. So I tried yesterday to make sure that every time I had a hypothesis, you saw immediately how it was going to be, but this time I had to wait. Great. All right. How much time do we have? Okay, 25 minutes, right? Great. Okay, we can do better. This is in fact the universal and excisive approximation to F. The proof of that is no different than the one I showed you for P1 yesterday. It's just showing that in fact we're going to get maps from F to PNF, and that if you have another map to another n excisive functor, then it's going to factor through PNF the same way that I showed you yesterday. So I declined to do it twice today. All right, but now just observe that because I started with strongly co-Cartesian cubes, all my faces are push-outs, but that also means that subcubes are push-outs in general. And the consequence of that is that if I start with something that's n excisive, in fact, it's m excisive for every bigger m. I say n and m like they sound like the same letter, so on the slide it's n and n plus k instead, same idea, okay? So that means that if I take the map that I get from the fact that this is the universal, sorry, I can't write and talk at the same time apparently. If I take the maps that I get from this being the universal n or n plus k excisive thing, this thing is also a new map to an n plus k excisive functor. And by universality, that means that it has to factor through. So I'm going to get a map here that I'll call Q. Well, this is the easy way to show that in fact you get a whole tower. Okay. So not only do I have an excisive approximation for each degree n, I get the whole tower worth of approximations. And in the best case, the idea of this tower is that it converges. In other words, we hope that if I go to the limit of the tower, whatever there is up there at p infinity, that I get back f of x. That's not always the case, and it's okay that it's not always the case. It turns out this tower has lots of interesting things in it, even when it doesn't converge. But if it does converge, what we just did was take a functor and figure out a way to approximate it by functors that are determined by their value on n points. That's often simpler to compute than whatever the f was that I started with. And so that's the idea of why we do calculus to begin with. Okay, now it says the Taylor Tower. And I'm very grateful because Connor introduced why this is called the Taylor Tower yesterday, but I feel like I should tell you a little bit more. So we're going to define some layers. So for each of those maps from Pn to Pn minus 1, I can take the homotopy fiber. I think I haven't said homotopy fiber yet. And in case you have never seen it before, all I mean is that I have a map from PNF to Pn minus 1f. everybody in sight is base pointed. So I always have a map from the base point in, and I just take the homotopy limit of that diagram. Okay, later I'm gonna say total fiber, and please remind me in case I forget to say what that is. Okay. That's consistent with what we said for D1F. So this definition of PNF is as a sanity check, we've got kind of the same thing going on. And just for vocabulary, a functor F is n reduced if its Pn minus 1 is contractible. A functor which is both n excisive and n reduced is going to be called n homogeneous. And we want these to be n homogeneous. Okay, let's see. They are. Hooray.
Sorry.
All right, so DNF is n homogeneous. I have to show you that it is reduced. So homotopy limits of n excisive functors are n excisive always. I'm taking a limit now, so I don't even have to worry about doing anything fancy. And for this one, so that means that it satisfies the first criterion. The second criterion says that this thing should be contractible. Okay, well, consider the map Pn of Pn minus 1f to Pn of Pn minus 1 of Pn minus 1f. That was harder to say than I thought it would be. Okay, so all I'm doing is applying the functor Pn minus 1 to the little map, which I think I called these Q's. Qn minus 1. All right, well, this is the n minus first approximation of a degree n minus 1, or of an n minus 1 excisive functor. So this one is just Pn minus 1f. This is the n minus 1 approximation of a degree n functor, which it turns out is also Pn minus 1f. This map is an equivalence. So its homotopy fiber is contractible. So it's homogeneous. All right, but that is just the first part of what we want in order to justify using the language, the Taylor tower. So we'd like to know that that tower of functors has a special form. I've shown you that the layers are n homogeneous, but in fact, they have a special expression. So as Connor mentioned yesterday, this is some kind of nth derivative or differential. The symmetric group has to act on it. It's a spectrum. That's why there's an omega sitting here. You notice that I told you as a spoiler that I was going to go back to top. Here we are. We're in functors from top to top. Okay. The omega is there because of the fact that DNF is in general a spectrum and spaces aren't, so we have to fix it. It has to have an action of the nth symmetric group, and I act on xn by permuting the n different copies of x. All right, so what is this supposed to evoke? That thing that I told you was called the nth derivative is supposed to evoke an actual nth derivative if these were functions instead of functors. Taking x and smashing with it itself n times is supposed to evoke taking the nth power of a variable x. Here I'm thinking about f as, again, being my little f's are always functors from R to R. My homotopy orbits, well, that's supposed to be something like dividing by n factorial. Count up how many different ways there were of permuting my variables x when I take x to the n, and there were n factorial of those, and I divide it out by that. That is exactly because I'm taking some kind of homotopy orbit action. And so what I am looking at is that DNF, except for the part about I'm dealing with spectra and I have to deloop, or I have to take omega infinity, whatever, loops infinity. This is supposed to look like taking the nth derivative at a point multiplying by x to the n and dividing by n factorial. Okay, and so the fact that there is this resemblance between these two is the reason that we call this the Taylor tower. Great. Now, why do we have this resemblance between these two? So anybody who's in this room who knows the answer knows that I can't tell you in 15 minutes the answer to that question. So I'm going to give you a sketch of why you should believe it, that tells you a little bit about why you should believe this, why you should believe an n-homogeneous thing has a particular form for functions. I can't really fully do justice to the whole thing, but if I wanted to think categorically, what I'm doing at this point is basically giving you a guide to reading this part of Goodwillie's papers, as opposed to telling you what's in Goodwillie's papers. And so the guide would tell you that there's a four-way equivalence of functors. So on the right-hand side, let me start with n-homogeneous functors. From top to spectra. And I just told you that my derivatives are going to take value in spectra. And so you should expect that I need to think about spectra here. Now, if you don't want to deal with topological spaces and spectra, because I promised you we could be doing this more generally, you can, but it's easier for me to think about this in top, so I did. But what you should do instead is make sure that you have your base pointed category in place of top, and whatever goes on the right-hand side is its stabilization. Okay. On the bottom, I'm going to have symmetric multilinear functors from top star to spectra. And I'm going to show you, maybe somewhat convincingly, that there's an equivalence between these two categories. The downward facing functor is going to be called CRN, or the nth cross effect. The upward facing functor is the diagonal, and I'll try to convince you that that's an equivalence. All right, but then I have to deal with the fact that I really shouldn't just do this for spectra. So that word is supposed to be homogeneous. I should be looking at functors from top star to top star instead, and I take the same version of these categories down below. So here I'll have symmetric multilinear functors from top star to top star. Over Y, top.
Symmetric multilinear functor, several variables, no?
Symmetric multilinear, yeah. So I'm doing this all with some fixed n in mind. That's n was reflected in the cross effects. You're right that what I'm doing here, yeah, you're right that this is multilinear functor of n variables. On both sides. Yeah, I didn't say it, but you're right. Okay. I have a cross effect here too. There's somebody here. Here, to get a symmetric multilinear functor from top star to spectra, you just do what I showed you in the formula, apply omega infinity. And there's somebody here. Okay, same thing here. I think I even, when I originally made this diagram, I think I put them in the right orders so that, you know, these are adjoints, and I think that there's some convention here about who's right and who's left, but I don't remember what it is right now, so we won't dwell on it. Okay, so let me try to convince you about this one. And then I'm going to tell you why this is hard and why I don't want to tell you what all those question marks are. Okay. Okay, so here's the motivation for functions. Let's start with regular polynomial functions from R to R. And I'm gonna define, so everything on the slide is always a polynomial. Okay, so not, sine and cosine have no place in functor calculus. That's probably not true. I'm gonna regret it one day, but I don't need it today. Okay, so I'm gonna define the second cross effect by the formula that you see in front of you. Take two variables, x and y, and think about all of the ways that you might try to add them together. I told you yesterday that the second cross effect was going to measure the failure of f to be linear. And so that's what it's doing. It says add x and y together, just like we did when we were thinking about additive functions. Subtract off the difference, and then you have to fix it because maybe it didn't send 0 to 0. Okay, if that sends 0 to 0, then you don't need that last term. All right, then suppose that it turns out that I started with any degree 2 polynomial function. The second cross effect is going to kill anything that's a homogeneous term. So it's killing all of the terms that are just x, all of the terms that are just y, all of the constants, and the only thing that's left is the cross term. Okay, so as a result, when you work out what that is, if it turns out you started with a homogeneous degree 2 function, then you can completely recover that function from its cross effect. A degree 2 homogeneous function has the property that it's equal to 1/2 the cross effect evaluated at the same variable twice. If it turns out that it wasn't homogeneous, then you run into trouble because I didn't pick up the lower degree terms. So if it was just degree 2, it doesn't work. If it turns out it's polynomial of a larger degree, it doesn't work because then I have this higher dimensional stuff that's getting in the way that the taking the x plus y didn't kill. So this is really special to being homogeneous. Okay, that's exactly the kind of thing that I would need in order to show that equivalence. What we just did was start with a homogeneous function, and we've now produced a function of 2 variables, which might have some properties that were the words on my board. We'll get to that. And we were able to show that it recovers it. Okay, so this is an isomorphism between the set of homogeneous degree 2 polynomials and some sort of degree 2 functions. Okay, what sort of degree 2 functions? We'll notice from my formula that the cross effect is symmetric. The roles of x and y didn't matter. And notice that from my definition, because I just got that cross term 2axy left over, that thing is additive in each of x and y. It's linear in this case because it's also going to have the property that it sends f of 0y to 0 and f of x 0 to 0. So the thing is multilinear, meaning it's linear in each variable. In other words, the set of homogeneous degree 2 functions is isomorphic to the set of symmetric multilinear functions of 2 variables. And that's going to be true in general. So this thing that I did where I took the alternating sum depending on how I broke up the sums, you can generalize that to what had happened if I added up n different variables. Instead of 2 variables, you will get a thing called the nth cross effect. And it will recover homogeneous degree n functors, but with this factor, 1 over n factorial. All right, well, we know what 1 over n factorial is supposed to do. If it turns out I'm thinking topologically or categorically, there's a symmetric group action happening there. The symmetric group action is happening because I can permute the x and the y in the case that I gave you. And you can see where if I went 1 higher, you would see that there were factors that were switched. There are summands that were switched when it turns out that I made those kinds of permutations. Okay. I don't remember what I said next because after this I have to wave my hands a lot. All right, so here's how we do it topologically. I can define a cross effect functor, and I define my cross effect functor by being the total homotopy fiber of the cube that I get by taking coproducts of spaces. So if I just do this, oh, we switched to green. If I just do this for n equals 2, then what I'm looking at is the cubical diagram where I take the sum f of x plus y, f of x, f of y, f of a point. Take the total homotopy fiber of that cube. There's a choice for what you want to call, how I want to, it's a total homotopy fiber. There's a choice of how you describe the total homotopy fiber. So I'll just take the pullback of the diagram that I get when I delete the initial vertex. There is an induced map from f of x plus y to p. So my CR2 f of xy is just the homotopy fiber of that map. So we have cross effects in this case, and they're given by looking at addition of some variables and looking at the difference between that particular if I didn't have the f's here, I had a push out diagram. So what we're looking at is the difference between this taking certain push out diagrams to pull back diagrams. Great. What's the next slide say? Great. It's symmetric and multilinear. I think I'm not going to say anything more about that. Okay. And then it says the end. So I think what I meant to do here was say, okay, so so it's symmetric and multilinear, and the reason that you should believe what we had before is that now what I've shown you is a way of producing from my original diagram. Let's see if I can just grab it. So what I wanted to do was try to convince you why this was supposed to be true. Well, we'll just do it from here. That means, so when I constructed the cross effects, now I've given you this functor down. Highlighter. There we go. Okay. And the functor up is just the diagonal. And what that tells me is that I should expect that DNF, nope. Which is a homogeneous functor, it should be equivalent to the nth cross effect. Okay, so where does this expectation come from? This is using the motivation from functions. It should be equivalent to the nth cross effect of f evaluated. So let's put an x in here because I'm going to evaluate on a diagonal. And then I'm going to take some homotopy orbits because that's my version of divide by n factorial. Okay, and so that's close enough to what I want to say about why you should believe that that equivalence is there. And if I work a little bit harder, then I can do a little better. So this thing turns out to be, I don't want to do better. I don't want to get into it because I'm gonna screw things up. But if I work a little bit harder, I can get this into the form where it turns out that this looks like a derivative times x to the n mod the homotopy orbits. Okay, so this is the core part of that argument. But what I wanted to say is that this argument should only convince you about the part of the argument that has to do with spectra, and the reason is because since spectra are stable, push out homotopy co-Cartesian diagrams are homotopy Cartesian. And I have homotopy orbits here. They are special versions of homotopy colimits. It's just a special kind of a homotopy colimit. They don't commute with the property that makes something Cartesian because I needed to take the pullback there. So when I'm in spectra, the fact that I took these homotopy orbits don't get in the way of what I would want to do to take that and turn it into the form that Connor showed yesterday. But when I'm in spaces, that's a problem. And so you have to do quite a bit of work to try to figure out how to make that go. It does go, but it takes a little work. Okay, so that is the Taylor Tower, as much of it as I'm going to talk to you about today. So we have a definition of what it means to be our polynomial degree n being n excisive. We have a reason that this looks formally like Taylor Towers from our calculus 1 classes. whichever class you teach it in. And tomorrow I'm gonna show you some of the other things that you can do with this. Thanks. Guess I didn't have to put that away.
Question, I don't wanna sound like I'm crazy for asking it. So, you try and explain why I'm thinking this way. My first question was, what spectra can appear as coefficients in like these homogeneous terms in the Taylor approximation, but I figure if they're using the analogy with calculus, it could be like any spectrum you want at any point in the approximation. And so then my next question was, what if we're looking at like a G Goodwillie, like an equivariant Goodwillie tower for like G spaces and G spectra? I'm assuming that's a thing that exists. I don't really know. But when I was asked this question in my head, I thought, okay, in the ordinary case, you have this Goodwillie tower, either of functors two spaces or spectra. So tower of spaces or spectra, and when I think of a tower of spectra, I know that I don't know much about the Goodwillie tower, but I know that its conversion properties, you study it, making like some connectivity estimates, so somehow it's related to like the Polynomial filtration maybe, which ordinarily is quite nice, because it's like, if you take this, the Polynomial filtration and look at like the corresponding T structure, and you look at its shifts and its parts, it always looks like abelian groups, which is very, very different in the equivariant case, because if you equivariant, you have the slice filtration, and if you look at corresponding T structures and you take successive parts, they actually change as you go along the layers. And I'm wondering if that affects the answer to this question, equivariant.
Okay.
What?
Okay, that was a lot of thoughts, so I'm sorry for cutting you off, but I wanna be able to address some of them before I forget what they were. So, the first thing. I already forgot. The first thing you asked me was what kind of spectrum? So if it turns out, so remember in the first lecture, I said a good example of a one excisive functor is a spectrum smash X. And so from that one, yes, I can get any kind of spectra, but I don't get every kind of spectra showing up in this layer way that I wanted, because they have to have an action of sigma n on them. So the spectra that show up as derivatives have to, at the very least, have an action of the n symmetric group. So that limits things. Okay. And then I could do, I think what you're suggesting, which is I could start to try to build degree n functors by just specifying lists of spectra with the right kinds of actions, by taking the sum of them as I go, or taking the product of them as I go. Okay, so that was the first thing. The second thing you asked is about, is there such a thing as a Goodwillie calculus equivariant, an equivariant Goodwillie calculus? Not that I know. So the answer to the rest of what you said is, I think some people are thinking about that, and I think that for good reason, because Angelica is going to be one of the leaders of a group that one of the things that group is thinking about over the next couple of years is equivariance and Goodwillie towers.
I forgot what you were talking about.
So there's a collaborative research group led by Martin Franklin, Don Stanley, Angelica Osorno, and I think there's going to be some activity in this over the next couple of years. Come to Canada with that.
Okay, thanks.
Yeah, so I can't, like I said, I can't say much about the rest. That was a good question, thank you.
Other questions? Okay, let's thank Kristine.